Do you hear me? Now it's better? Okay. So this talk is about blame assignment of a higher order contract system that contains two new operators, intersection and union. Before I go to the specification of the new operators, I briefly recall the existing contract notations. And yeah, first let's define them flat contracts. Flat contracts are the fundamental building blocks of all other contracts, and they simply consist of a predicate. And here we have two flat contracts, an even contract that checks for even numbers and an odd contract that checks for odd numbers. Then as a running example, now let's consider the x plus 2 function, or function that takes an argument and adds 2 to its argument. And then we assert a contract to this function, a function contract. And in my talk I use this @ sign to assert a contract to some subject. And yeah, this is a function contract. A function contract is built from two contracts, one for the range and one for the domain of a function. Yeah, and in this case, both are flat contracts. So we restrict the function arguments to even numbers, and yeah, the function has to return an even number. Yeah, and if we assert a contract to some function or some value, then we get a contracted version, and then here if we call this contracted function with the value 2, we see that the contract is satisfied and the function returns 4, and 2 and 4 are even numbers, so the contract is happy. But if we try to call the function with the value 1, we get a context blame because the context calls this function with a value that does not fit to the specification of the contract. Yeah, now let's try another contract for the function. Here I assert a function contract to this function that restricts to odd numbers. Then I'm able to call this function with the value 1, and the function returns 3. 1 and 3 are odd numbers, so the contract is satisfied. But now I'm still not able to call this function with the value 2. So in this situation, I would get a context blame for calling the function with the wrong argument. Okay, what we get from this example is that the given function works for even and for odd numbers. Or more precisely, it also fulfills the odd to odd and the even to even contract, because for odd numbers it returns an odd number, and for an even number it returns an even number. So the question is, how can we express this with one single contract? And what we would like to have is some kind of intersection contract between both function contracts. Yet the inspiration of an intersection contract is drawn from the corresponding operator in type theory. So in type theory we have intersection and union, and for example if a value has two types, S and T, then it also has the intersection type. Or from the context perspective, if a value has an intersection type, then the value can treat this value as an element of type S or an element of type T. And this is used to model overloading and for multiple inheritances of values. Unions are the dual of intersection, and they model the domain of overloaded functions. And for example, if a value has a type S, then it also has the union type of this type S and some arbitrary other type. And for the context did not really know which type the function has at the end. This work extends higher order contracts with the ability to have intersections and unions of contracts, and the specification of both contracts is based on the corresponding type theoretic operator. So what we get at the end is an intersection contract, for example the intersection of both function contracts that we have seen before, and then we are able to call the contracted function with the value 2 and the value 1, and we did not get a context blame simply because of the intersection. Now let's going a little bit closer to the specification of intersection and union contracts, and because of the time restriction I only focus on intersection, but the union contracts are the exact dual of the intersection contracts. For flat contracts, where we can build the intersection of two flat contracts, for example the intersection of pos and even. Here pos is another flat contract that simply checks for positive numbers, and this contract is satisfied by every positive and even number. Yeah, and for flat contracts, it's easy to see that the intersection of two flat contracts is equivalent to the conjunction of the contained predicates, simply because the subject needs to fulfill both contracts. But for higher order contracts, it's a little bit more complicated. Here I have chosen another example, a function that takes an argument and adds 1 to its argument, and I assert a contract to this function. This is an intersection contract between one function contract that restricts to even numbers and one contract that restricts to positive numbers. Yeah, when calling this function with the value 3, the function returns 4. And if we look to the contract specification, then we see that the domain contract of the left function contract fails, but the right function contract is satisfied. And as I mentioned before, the context is allowed to choose which side it would like to fulfill. So at the end, this contract is satisfied. Yeah, when calling the function with the value -1, we get a context blame as expected, because -1 is neither even nor pos. And the specification for blame says that the context of such an intersection contract gets blamed exactly if the context gets blamed for the C contract or the left contract and for the right contract. Yeah, and if we call this function with the value 2, then we see that our contract system gives us a subject blame. And the reason is that the subject of an intersection needs to fulfill both sides. So for even numbers, it has to return even numbers, and for positive numbers, it has to return positive numbers. Yeah, and in this example, we call the function with the value 2, and the value 2 is even and pos. But the function attempts to return 3, and 3 is not an even number, so the subject gets blamed for not returning an even number. And the specification simply says that the subject gets blamed for an intersection contract C intersected D exactly if the subject gets blamed for C or it gets blamed for D. So it needs to fulfill both sides. Yeah, when implementing such an intersection and union contract, we run into a problem. Let's go back to the example we have seen on the slide before. The function that computes x plus 1 contracted with the intersection contract, and we call this function with the value 3. Then when checking this contract, the implementation needs to choose an order in which the contained contracts are checked. So for example, let's choose the even contract or the domain contract of the left function contract to be the first contract that is checked. Then we see that this contract fails, and thus the left function contract will throw a violation that blames the context for calling this function with an element that does not fit to the specification. But in this situation, the contract system is not allowed to throw in violation simply because this function contract may be nested in an intersection or a union. So it still needs to wait, and next we check, for example, the domain contract of the right function contract. This is satisfied because 3 is a positive number. The function then returns 4, and then also the range contract of the right function contract is satisfied, and because the context is allowed to choose, at the end, this contract is satisfied. So a failing contract is not allowed to throw in violation immediately. And the final violation of such a contract depends on combinations of failures in different subcontracts. And this at the end requires that the contract system is able to connect the outcome of each particular contract and to combine this with the enclosing operator. To demonstrate, I show a small step reduction that reduces an expression and a constraint set to a new expression and a new constraint set. And the idea is very simple, that if a contract gets unrolled or a predicate gets checked, we do not throw a violation if a contract fails, we simply create a constraint. This means, if we unroll an intersection contract, we create a constraint that connects the outcome of both subcontracts, and if we evaluate a flat contract, then we only create a constraint with the outcome of the flat contract. And the final blame calculation at the end happens only in respect to this constraint list. Now I'll show some evaluation rules that demonstrate how this works. But I have to mention that these evaluation rules are simplified, and if someone is interested in the full evaluation rule, then the best is to have a look to the paper. Yeah, here we have the evaluation of a flat contract that is asserted to some value, and now the @ is adorned with some blame labels that represents the current contract assertion. We have a constraint set, and the first thing that we do is we evaluate the predicate, we get some result, and then we go and create a constraint that maps the outcome of this of the predicate's evaluation to the current blame label, and this constraint extends our existing constraint set, and then we simply proceed with the new constraint set. So in this situation, we do not look to the value and we do not throw in violation if the predicate evaluates to false. An interpretation of such a constraint list at the end is simply a mapping from blame labels to elements of a Boolean logic. And in this logic, we say that true is subset of false, and this ordering is required to reflect the gathering of new information during different execution steps. And each blame label is associated with two fields, a context field and a subject field, and the meaning of the fields is as follows. If the subject field is false, then a subcontract or a contract fails, blaming its subject, and if the context field is false, then a contract fails, blaming its context. Yeah, let's look how the constraint satisfaction works. This constraint satisfaction is modeled by this relation. Here we have exactly a constraint that comes from the evaluation of a flat contract, for example, from this one. And yeah, exactly the subject field is equivalent to the outcome of the predicate, and the context of a flat contract is always true, simply because every context respects a flat contract. Yeah, and finally, we need something to define. We need to define something when to stop and when to throw in violation, and thus we need to define when such a constraint list is in a blame state, and this is the case if either the subject field or the context field maps to false. Yeah, and if this happens, then our evaluation has enough information to say, okay, now we can stop and we can throw in violation and blame someone for violating a contract. Yeah, now let's have a look to the evaluation rules of function and intersection. Here I have the assertion of a function contract, and for a function contract I need to wait until the function is called. So I have a function application, I have a constraint set, and the first thing I do is I create two new blame labels, and then I create a function constraint that maps the outcome of both labels to the current label of the current assertion. And this constraint extends my constraint set, and then I simply proceed with asserting the domain contract to the function argument and the range contract to the function's return. Yeah, and the constraint satisfaction of such a function constraint says that the subject field is equivalent to the conjunction of B1 context and the implication between B1 subject and B2 subject, and this means that a function is responsible for using the argument corresponding to its specification, and in case that the function is called with the right argument, then the function has to return an element corresponding to its specification. And for the context, it's simply the conjunction between B1 subject and B2 context. This means the context of a function is responsible for calling the function with an argument corresponding to its specification and to use the function's return corresponding to its specification. For intersection, it's very similar. Here I have the assertion of an intersection contract. I also have a function application, so because for each application I can choose which side I would like to fulfill. I first create two new constraints, two new labels and a new constraint that maps the outcome of both subcontracts to the current assertion, and then I simply proceed with a sequential assertion of both contracts that are contained in the intersection. And the constraint satisfaction is, as I've shown before, the subject is the intersection of both, the conjunction of both subject fields, and the context is the disjunction of both context fields. Yeah, now some words to the union contract. The union is the equivalent dual of the intersection contract. This means that in the specification, all conjunctions and disjunctions have to be exchanged. And the delayed evaluation of an intersection contract flips to an immediate evaluation. Delayed evaluation means that every time a contracted function is used, the context is allowed to choose, and this flips to an immediate evaluation. Yeah, in the paper, you will find some more technical results. For example, some contract rewriting rules that are required to pull out unions out of intersections so that the immediate parts can be, the constraints for immediate parts are created at assertion time and only the delayed parts remain. The paper also contains a deterministic and a non-deterministic specification of our contract monitoring and a novel denotational specification of the semantics of contracts. And it also contains some theorems for contract soundness and for blame soundness. So now I come to the end. We have seen intersection and union contracts that provide the dynamic guarantees equivalent to the corresponding type-theoretic counterparts. We have a novel constraint-based blame calculation that allows us to have unrestricted intersection and union. And unrestricted in this case means that we can have the intersection of a flat contract and a function contract, or the intersection of two function contracts with different arities. Yeah, and the calculus that we have seen is implemented in 3JS. This is a language-embedded higher-order contract system for JavaScript. Thank you for your attention.
So thanks, this is very cool and solves important open problems in contracts. So you didn't talk about dependent function contracts at all. Is that possible in this system? Are there additional complications here?
No, there are no additional complications because a dependent contract also reports two fields, a context field and a subject field, and those they can be combined with every other contract.
Because looking at your rule for intersection, it seemed a little, what if the dependent part of the contract for the right-hand side of the intersection doesn't treat the value according to the left-hand side of the intersection? It seems like that would result in blame, potentially, or something going wrong in your setting.
So you mean if the contracted value from the left side flows into the dependent part?
Yeah.
Yeah, so we have different evaluation semantics for this. So we either remove this contract and the dependent contract will not see the contracted version, or the contract remains, and so we see the violation at the end.
And have you thought about proving the sort of Demulis's various kinds of contract correctness for those semantics?
You mean the INDI specification?
Or more generally, the completeness and complete monitoring and blame correctness results? Thanks.
Other questions? Okay, let's thank the speaker.